going to record a backup as well. Okay, the way that we would do previously. Okay, do you remember what we were doing?
Mass spectrometry.
Yeah, and what was the whole point of mass spectrometry? What was the point?
It splits up. It's either different.
Yeah, it takes a molecule and it smashes it to pieces, and depending on which technique you use, whether it's the EI or the CI or something in between, you get different degrees of fragmentation. Okay. So what we should probably do is take a look at what some fragmentation patterns look like and use those as a diagnostic of figuring out what our molecules actually are. Because ultimately, what we want is this to be a technique that does one of two things. Either confirms what we thought that we knew. Hey, I think I've made aspirin. I'm going to stick it in this instrument and let the instrument prove to me that I've made pure aspirin. Or I've made a brand new thing and I don't know what it is, and I'm going to use this technique to help me find out what is inside it. And in the same way that infrared will tell us that there's a particular functionality, a particular type of group in our molecule, and NMR tells us that we have these groups and their interconnectedness, what mass spec does is it tells us these are the fragments that you get when you take your molecule and you smash it into pieces. So it's a jigsaw puzzle. Doesn't necessarily tell us connectedness. So if I can smash my molecule into multiple methyls, it tells me that I have lots of methyls, but it doesn't tell me what they were connected to. NMR does that. Okay, let's just do a quick recap of what we have. So I have a baseline, and I measure M over Z. And, okay, so M, we know what M is. What's M?
The mass.
Yeah, mass. What was Z? What was Z?
Nuclear charge.
It's charge. And what's that charge going to be? When I take... Go ahead, you were talking.
The +1.
It's +1 because I'm going to take my molecule. Can you see the top of the board? Yeah. And I'm going to bombard it with electrons, and I'm going to convert it into a radical cation. The electron that comes in is going to be at a sufficient energy that it doesn't get encapsulated, it doesn't get captured by this molecule. It knocks an electron out of this molecule. So now my molecule has an unpaired number of electrons, probably. Did it start with an odd number or did it start with an even number? It probably started with an even number. but they don't all. If it did start with an even number, now it has an odd number. And the odd number versus even number is something that we'll come back to later on. So I've dislodged an electron, so now I have 2 electrons floating around. And I've made a radical cation. And so my Z is my charge is +1. So this M over Z is my mass divided by +1. So it's mass, right? This is a mass scale. And then I have really an arbitrary number right here on the y-axis that just reads amount. It's the amount detected. And a mass spectrum might look like this. It gives us lines, and those lines happen in fragments. They tend to be in little clumps, and there are 2 things that we immediately need to pay attention to. This one and that one. From left to right, what's this one called? Michael, your microphone icon came on, but we didn't hear anything. Alden, go ahead. If you're talking, Michael, we can't hear you. I can't hear you. Matt, go ahead. Did we perhaps lose audio? Everybody speak at the same time. No, I'm not hearing anything. Okay, hold on. Okay, try that again. Come on now. I cannot hear anybody talking. Okay, let me see. Oh, is that real? Okay, one moment. I'm going to jump out, jump back in again. Oh boy. Okay, how are we doing?
Let me check.
Okay, I can hear people now.
Oh. That's cute. He's not happy. Huh. I woke my dog up this morning to show to show her to the rest of my anatomy class.
All right, cute dog.
Thank you. Can you hear us?
Yes, I can. All right.
Oh, perfect.
Yeah, it just needed another reset. I think this might be just something we have to live with. Okay, what's that called?
Base peak.
That's the base peak. That's the most abundant, right? And then what's this one?
Which one? I can't see.
I know, I got my hand in the way now. So the base peak is the most abundant, and we're going to set its height arbitrarily to 100. Move my head out of the way. 100 on this scale is the height of the base peak. Okay. What's it called here? This one that is the heaviest.
That's the unfragmented mass.
Mm-hmm. And we give that a name.
Peak at the peak at the highest.
Mm-hmm.
The molecular ion.
That's called the molecular ion. Yeah. Okay. So this is basically just unfragmented. All right. Here's a question. Can anything be heavier than the molecular ion? Stunned into silence. Can anything be heavier than the molecular ion? That sounds like a yes or no question. Oh, did we lose you
I'd
again?
like to pull it. I'll say yes. I'll say yes.
Yes. Yeah. How is that possible? How is it possible to have something that is heavier than the unfragmented molecule that you start with? How is that possible? Can you see the molecule I wrote on the board?
Yes.
What's the name of the molecule that I wrote on the board?
Chloroethane.
There you go. Chloroethane. 2 carbons, 1 chlorine, 5 hydrogens. What would be the value ascribed to the molecular ion for chloroethane? Oh, go think. You might need a pencil. I want to know what the value in mass spec of the molecular ion for chloroethane is. And I'm prepared to wait. How would we even know? You shouldn't need a periodic table. the mass of carbon is 12. Yes? The mass of hydrogen is 1. What's the mass of chlorine? What's the atomic mass of chlorine? They're dropping like flies. What's the atomic mass of chlorine? Come on.
35.
I didn't catch that.
35.
35. What does it say on the periodic table for the atomic mass of chlorine?
Oh, hold on, let me look it up.
Yeah.
35.453.
Yeah, can't have that. Can't have that. How
Okay.
can I have, so what is it that makes up the atomic mass of a particular atom?
The weight of the protons and electrons.
No.
I mean neutrons. Sorry.
Yeah. Electrons weigh, you need 2,000 electrons. You need 1,837 electrons to weigh the same as a proton, so that's not going to matter. It's the number of protons and neutrons, and because those are integer values, I can never have a fractional number. It's not possible. The number that's on the periodic table is a weighted average of the isotopes of chlorine. And the two common isotopes of chlorine are 35 and 37. So, with 35 being the most abundant of the two, right? Which is why my number 35.45 for my atomic mass from the periodic table, which is really a relative mass because it's a weighted average, is 35.45. It's closer to 35. It's closer to 35 than it is to 37 because 35 is the more abundant of those two isotopes. But there is a real amount of 37 floating around in the universe. There it is. It's right there. And we can use this difference right here to let us know what's going on. When that chlorine, so there'll be a gap, there'll be a space in the middle, and these two lines will be two atomic mass numbers separated from each other. And anything, when it splits apart, anything that's holding on to that chlorine will see that fragmentation pattern be consistent. And because we know that carbon is 12, but there's a little bit of 13 out there. There's a little bit. You know, it was about a percentage, wasn't it? There's about a percent of carbon 13. If I see a little notch to the right, heavier than my molecular ion, I know that that's probably the carbon 13 kicking in, but I don't count this as being the molecular ion. I count the larger of the two things that are at the higher, and I'm going to count that as being an isotopic little tag. Okay? All right, let's look. Let's think about some fragmentations. So when it comes to the molecular ion, that's our heaviest signal. It's our unfragmented molecule. But be aware that there is the possibility of having something slightly heavier because of an isotope. And there's a little rule later on that if you divide the height of this by like the 1.1% that there is of carbon-13, you can actually figure out what the total number of carbons are in your molecule. Okay. Okay, so let's start about thinking about smashing these molecules to pieces and what that would look like. If I had a long chain alkane, this is only a small molecule, but it's just a chain, there's not really much that can go on here. I'm going to be doing this process. I'm going to take my molecule, going to add an electron, and I'm going to generate a radical cation and eject an additional electron, which means I'm going to break this thing into fragments. And it's possible that I could break that into small fragments, like this, or into slightly larger fragments. Actually, I'm going to do this one at the end, right here, so that I have a definite place for it. Like that. My mass spectrum might be able to detect both of these. What would be the mass of this fragment? This one right here. What's its mass?
15.
15. And then when I divide it by its charge, what's its charge?
It's 1.
Yeah, so 15 divided by 1 is just 15. If I see something at 15, that's a methyl. Now, even though you know that you have methyls in your molecule, you might not get to see them because they're small and they're a gas, and they might be lost to the vacuum because they are so small. Plus, remember, it depends what technique we used to do the ionization. Before we broke up, we talked about there being EI, electron impact, and CI, chemical ionization. EI is going to smash the molecule to pieces, but CI did a much softer break, and the agents that we used to transfer that ionization into our molecule might have been a methane in the first place. So there's a chance that we don't get to see that at all. What about this? What's the atomic mass of this thing? 29. 29 is going to be larger than 15. If I get to see 15 at all, why would 29 be a larger, more abundant peak than 15? What's the thing going on here? What's the underlying rule that says there should be more of this visible than that? Do you get it? That's a primary carbocation. This is a methyl carbocation. And carbocation stability says tertiaries are better than secondaries, are better than primaries, are better than methyls. Yeah? Okay. So that pentane, 1, 2, 3, 4, 5, that I made here, could fragment into a 3-carbon block. It could fragment into a 4-carbon block. It could fragment into a 2-carbon block. So what I would be expecting to see would be lines. And what would the interval between those lines be? The interval between 15 and 29 is what?
14.
14. What signal should be here? That would be a 3-carbon fragment, which would be this 14 plus that 14 plus this 15. 14.
43.
Yeah.
4. Oh, wait, 43.
Let me think. 12, 24, 34.
Is it 14?
Hang on. Yes. 14 and 14 is 28. And then 15 is my 43. Okay. That's a 3-carbon fragment. What about a 4-carbon fragment?
57.
Yeah. And then the molecular ion. The molecular ion is, how heavy is C5H12? 5 12s are 60 plus 12 ones, 72. Okay. This is an alkane. I'm seeing, or should be expecting to see, CH2 fragmentation coming off that molecule in chunks. What's a CH2 called?
Methylene.
Methylene. Yeah. Yeah. Okay. Let's do an ever so slight tweak on this. And let's see if we can predict something different. 1, 2, 3, 4. 5. This is 2-methylbutane, but it's still C5H12, right? So its molecular ion is the same as it was in our previous example. But now we're going to see a heavier hand at play, because I can break that bond, I can break this bond, I can break that bond, and I can break that bond. But one of those is going to break preferentially. I'm going to call this A, B, C, and D. I can cleave this molecule into fragments A, B, C, or D. One of these is going to be preferred over the others. A, B, C, or D. Have a think. So my molecular ion is still at 72. But my base peak, there's going to be a very, very definite base peak in this molecule. One of these fragments is going to dominate over the others. Which one?
Won't the tertiary carbocation appear the most?
Yes. So, well, do I have a tertiary carbocation?
You have a tertiary carbon.
I do have a tertiary carbon, but when I smash the molecule, can I leave that tertiary carbon intact and put a charge on it?
I don't think so.
Oh,
No.
You have a secondary
Yes,
carbocation.
I can have a secondary carbocation. So you're spotting that I want the most substituted thing. So A, B, C, or D, which one of those bonds is most likely to break?
C.
C. If I take the path to break the bond that I've labeled, the pathway that I've labeled as C, I get two fragments. This is a secondary carbocation. That's the one I'm going to take. So this was a C3H. What am I looking at? 1, 2, 3, 4, 5, 6, 7. 3 carbons. 36. 36 plus the 7. We're back at 43. That 43 is going to be my base peak. Okay? The others might be down here. That's my base peak. Okay. Alkanes don't do things that are particularly interesting. They break in a pattern that is predictable. We're going to see little methylenes. We're going to typically see intervals, but look to see when you smash this thing apart what it is that you're most likely to see. Now, if you go and you read a chapter on mass spec interpretation, you'll find at the beginning of the interpretation part of the chapter that they outline all of these rules about do these small calculations before you start. And as a matter of fact, they do that in the NMR chapter as well. There are people I know that would not dream about sitting down to interpret an NMR before they have calculated the IHD, the index of hydrogen deficiency, which is another way of saying the units of unsaturation. They wouldn't start to figure out what it is that they have until they knew, does my molecule contain a double bond? Does my molecule contain a ring? And that's great. But sometimes you don't know. And in fact, in research, you never know. So these beginning parts where they lay down the fundamental rules of what to look for when you're doing your interpretation, to my mind, they kind of prejudice the jury a little bit. But in the real world, you're not particularly likely to know. So I'm going to run through a couple of these rules just to say them out loud. You can make of them what you will. Okay, so our molecules, they're going to be organic. They're going to contain lots of carbon, plenty of hydrogen. They might contain oxygen. Oxygen is an even-numbered atom, and it doesn't have much of an impact on what's going on in our molecule. They might contain sulfur. They might contain chlorine or bromine. Chlorine and bromine both have distinct isotopes that will show up as repeating little motifs in the fragmentation pattern. Okay. And a molecule might contain nitrogen, and there is a little twist with nitrogen. It's called the nitrogen rule, that if your molecule contains an even number of nitrogen atoms, then the mass, the nominal mass of your molecular ion will be an even number. And if the nitrogens in your molecule are an odd number, then you get an odd numbered molecular ion, you get an odd numbered fragmentation pattern. Okay. There are people out there that say, before you do anything at all, go ahead and calculate the index of hydrogen deficiency, which is something that if you wanted to look up, it would be really easy to do. You can do that either in an NMR chapter or in a mass spec chapter. It's not particularly difficult to do. You just count the number of hydrogens, carbons, nitrogens, and you subtract the numbers from each other, and it tells you what we're dealing with. I don't think it's completely necessary to do that. There is another little rule that says, we had these little 14 spacings here between our alkanes. There's something called the rule of 13, which says, think of the framework of your molecule as just carbons and hydrogens, and count those as 13s. And then look at what your molecular ion is, subtract as many numbers of 13 from it, and what the remaining number is, that's where all the interesting part of the molecule is, and you can construct the missing part from that. That's kind of a rule of thumb. I'm not sure that it's something that we're going to really super have to follow. And then there is a little rule, I think I've got it written down somewhere, about the number of carbons that are in the molecule. So if you look at the size of the molecular ion, and then the size of the molecular ion plus 1, because the molecular ion plus 1 is carbon 13. Now, we know that carbon 13 is 1% of the carbon that's out there. So anything that's included in M that is not carbons will not be represented in this other peak. So if I take the ratio of M over M plus 1, that can lead me to the number of carbons in my actual sample. Okay. All right, now fragmentation happens mostly by just simple sigma bond cleavage that we one of the things that if you start to look, yeah, Alden, go ahead.
Is the molecular ion always carbon? So is n+1 always 13?
So M is the molecular mass of our unfragmented molecule. If there is a smaller ion just to the right of it, one carbon heavier, then what that's likely to be representative of is your molecule is now large enough that we have another isotope of it floating around in solution that is that has one carbon in it. And because that carbon-13 only shows up 1% of the time, we can kind of just do a rule of thumb that if I take the height of my molecular ion and I divide it by the height of the molecular ion plus 1, which sometimes isn't there at all, sometimes it's just plain not there, then I can, as a guide, tell me what the total number of carbons is. So in a small molecule, like we're doing C5H12 a minute ago, 5 carbons, chances of you finding a carbon-13 in that molecule, not particularly high. So the molecular ion will be the molecular ion. But if I'm looking at a polymer that has, or an oligomer, or a small peptide that has 120 carbons in it, then I can expect to see a small isotopic bump just to its right. And when the molecules get larger, you do need the help I need something to help me along here to figure out how many carbons are in the total molecule. Okay, what I'm going to try and do next is, hold on, I'm going to have to move this camera. Stay. Oops. Everything's falling over. I'm going to see if I can pull up Okay. Let me see if I can do this. Bear with me. Plugged into the wrong computer. Ugh. Hold on. All right, almost. Okay. My 1980s computer out of the way. Can we see the board?
I see the mass spectrometry slide you're showing.
Okay. I'm going to scroll. Okay. So in order to do this, I have to... Blackboard doesn't give me a window so that I can see my own window. It makes it incredibly small. Okay, so here's a couple of questions on a worksheet that have answers. And it says, here's a molecule. It has an M over Z of 170. So for us, that means a molecular mass of 170 Daltons. And that molecular ion has an intensity of 100. So that means that it is the most abundant peak in the sample. And it has an M plus 1, that's 13 over 2. Oh, it also has an M plus 2 peak of 1. What is the molecular formula? Okay, so the fact that this is an even numbered implies that we have an even number of nitrogens in our molecule. Okay. An even number of nitrogens means 0 is an even number. Okay? The molecular ion for this particular molecule is its base peak. It is the most abundant peak. And then the peak that is at M plus 1 is likely, in all likelihood, because of carbon 13. So if I take, we're doing it a slightly different way right here. If I take the height of the isotopic peak and divide it by its abundance, which is 1.1, that comes out as 12, which tells me I have 12 carbons. All right, so if there are 12 carbons, and carbons weigh 12, 12 12s is 144, right? So 12 times 12 is 144. I had 170 Daltons to start with. Give me a pointer instead. So my molecular peak was 170. I know from my isotopic peak that I have 12 carbons. And 12 times 12 is 144, which means I have 26 Daltons remaining. Okay. If my molecule was an alkane, then it would be CnH2n plus 2. And for 12 carbons, that would mean 24 plus 2 is 26. So C12H26 is completely possible. It's completely possible. But the fact, what I would have to do is now go look at its fragmentation to rule out, is there something else in there? Are there double bonds and an oxygen as well? Because I can also make, out of the remaining 26, right? So I know I have 12 carbons. 12 times 12 is 144. 144 subtracted from 170 was 26. So I've got these 26 Daltons to play with, If I make them all hydrogens, I've got an alkane. But if one of them was an oxygen, that would mean I have 10 hydrogens left over. And is it possible, is it feasible, could I write down a molecule that is C12H10O? Well, yeah, maybe. So then I would have to go look at what the fragmentation pattern looks like. Okay? What else have I got? There's another one right here. Can you see that one? That is, I'm trying to get the glare off the screen a little bit. This is the same fundamental question. I'll make these available to you. And then, all right, let's see what I've got. Okay, all right, so this is a little bit like what we were talking about earlier. I have two molecules, sorry. And I want to know which of these is heptane and which of these is trimethylbutane. So these two molecules would both have the same formula mass, because heptane, 7 carbons, so CnH2n plus 2, 7 carbons, 16 hydrogens. Trimethylbutane is 7 carbons, 16 hydrogens. So these two have the same mass. But when I look at the mass spectrum of them, okay, so here on this side, on the right hand side of the board, there's my molecular ion. And then I have something right here at, what's that, like 57? And then there's something right there at 71. 57 to 71, what's the gap?
14.
It's 14. And guess what that gap is? And guess what this gap is? Yeah. Now there's a little bit of untidiness in here where there's a couple of things that are other possibilities. Go with the biggest peak. Usually go with the biggest peak. So this one here looks like chunk, 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 chunk. This looks to me like a straight chain that is fragmenting into place. And notice, I would be expecting my methyl radical carbocation to be right here. And I'm not seeing it. I'm not seeing it. There's a very, very small bump right there that is a tiny amount of methyl. It's either lost to the vacuum in the experiment, or it's not particularly likely. All right, when I look at the other one, so these are isomers of one another, structural isomers. This one doesn't go chunk by chunk, but it has this big peak right here at 57. And then there's another, so its base peak, the base peak here is 57. The base peak in my previous one was 44. Okay. 57 and 44 are separated by 13. Is that 43? Yeah, my bad. 43 and 57 separated by 14. That's a CH2. That's a methylene between these two. This is a larger chunk. So this one, if you think for a second what 2,2,3-trimethylbutane could give you when you fragment it, this is a bigger blob, for want of a better word, of carbons all stuck together. Okay, so we can tell the difference. Let's see if I can find one with some oxygen in it. Oh, so here's something with some chlorine. See this here? That's my molecular ion at 78. +2 for it is my isotopic label. And then here, whatever this fragment is, the chlorine is still in there. Because I can see that this peak and that peak have the same relationship as my molecular ion does. So I haven't lost my chlorine yet. This big jump all the way down to here is going to be with the loss of the chlorine. Okay. All right, here's an aromatic one, and we'll end with this. My molecular ion out here actually has 2 isotopic peaks. Molecular ion, this is my isotopic chlorine right here. It's separated by 2 Daltons. And then this one right here, that's my value due to carbon 13. So if I took that number and divided it by carbon 13's abundance, I would be able to figure out that there were 6 hydrogens, 6 carbons in this molecule. The other thing that we're going to see is that the mechanism for breaking aromatic rings apart is special, and that to break a ring you have to break, so even if I'm going to put my thumb over this, if I broke that bond, it doesn't change the mass of the ion that I'm looking at. If I want to change the mass of the ion that I'm looking at, I have to break 2 bonds. And so typically for rings, and because aromatics are stable, we see a very strong molecular ion at that mass. So rings are going to have a very strong molecular ion, and here at 78, that's 6 12s plus 5 hydrogens, making, what's that, 77? Yeah, 77 right here. That's my monosubstituted benzene, and expect that to be intact, and that's going to be a pretty intense band right there. Okay, so I'll throw a couple of these at you as a quiz in Blackboard. Nothing too particularly strong. I also have a chapter that I can upload to Blackboard as a PDF. That's a bit more than we need. If you can get through this chapter, then you can understand absolutely everything. Okay?
I have a question.
Yeah, go ahead.
What should we expect for like the rest of the class in terms of like grades?
Yeah, so I'm still waiting on what the university is negotiating with one of these online vendors. So we already have online classes that have the capacity to take online exams. And it is my understanding that we are talking with those people to allow us to give at least finals online, and that everybody gets to sit in front of the laptop and is monitored by a human while they take the test. that has yet to be announced to me by the university, so I don't know 100% where we are with that. You'll know when I know. So what we'll do as a method of assessment between now and the end, which is only 5 more lectures, between now and the end, is I'll write these into quizzes. You'll get a quiz, 1 or possibly even 2 quizzes a week over a topic, and that's now a proxy for your exam score. Because the prospect of us having 4 written paper tests has evaporated. There is still the possibility of you writing something, but not much. You know, the way that our tests were, and which I was talking with the organic students yesterday, is that, you know, in order to pass the test for organic, you have to scribble the structures out. We have no way of capturing that anymore, because you can't do that in Blackboard. You can't draw structures in Blackboard. So yeah, there's going to be a rethink, and it has to happen really soon. So when the university tells us that we have something in place that will allow us to have examinations, then you'll have an examination. But I only really think that you're going to have one. We'll put the rest of the work into quizzes and gradable, and anything else that's gradable through Blackboard.
Cool. Then what about portion? Is that kind of just the same thing?
About what?
The lab portion.
Well, yeah, that's pretty much history. I do have. It is possible we're going to do some X-ray diffraction. And X-ray diffraction is something that involves a small amount of mathematics that could be done as a worksheet and turned in as a lab. But there is no capacity for us to do any physical activity that you could purpose as a lab in this class anymore. It is gone.
Can we submit our last lab report that we did so we can get points for that?
Yes. Yeah, are you locked out?
Have I what?
Nice.
Are you locked
There's
out
not
of it?
suspicion yet on Blackboard.
You should have the ability for unlimited submissions. I don't believe I've locked you out.
Have
I
you
didn't see
opened
that.
Oh, then that's another question. Yeah, did I actually invent it before I locked you out? I don't know. I will look. The other thing that we'll do is keep an eye on the calendar. Blackboard has a calendar, and I'll write into the calendar just a note of, hey, this is what we're going to be doing in the immediate future. And just keep a track on that, because there might be a link or two in there that I want you to be aware of. Okay? We're going to make the best of it that we can.
If I have maybe questions or something about the quizzes or assignments, is there a way that we could do like office hours or something for this class? Yeah. Just like kind of how we did during the school year?
Yeah, so what we have right now, this shared teleconference, this is open without end. So if 2 of you were to decide, I would like to discuss this amongst ourselves, you can just log in to Blackboard, go to this particular teleconference collaborate site and put your cameras on and hold your pages up and share your homework amongst yourselves. So feel free to use this for your own purposes, and then shoot me a message that says, can you come into the classroom and discuss this with me? And as long as it isn't 11 a.m., where am I going to go? I'm locked in. So yeah, I'm probably available. Just shoot me a message, and I will come in, and we can work through problems. I got a whiteboard. We can chat it through. But it doesn't have to be just us. This is available for you to work amongst yourselves as well. This is open, and you can use it for whatever it is that you feel is necessary.
Okay, thank you. I was just wondering, it's harder for me to like retain the information this way, doing class this way. There's more distractions at my house and stuff.
Yeah.
So I think it would be helpful to have a time where we can talk and work through problems.
Yeah. Yeah. Just on demand. And if something comes up that is noteworthy, like you bring up a topic that we go, oh, I see, or two of you bring up the same topic, then I will throw that back out to the whole group as well. It's like, hey, everybody needs to get on board with this. But I don't want to put, one of the things that the university has made it clear to me is that we can do the online component of this class any way that I want to, with the exception of, if I hold class, it has to be at 11 a.m. on a Tuesday and a Thursday. Okay, so this right here that I'm doing, I am restricted. This can only be at this time, because I cannot take you away from something else that you have on your calendar. But if you come to me, I'm completely flexible at my end. Okay?
Okay, thank you.
Okay. All right. I'm gonna put some documents together, and I'll talk to you all soon.
Okay,
Right.
sounds good.
Thanks for joining.
Alright. Thank you.
Bye.
Okay, bye-bye.
Thank you. Bye.
Bye-bye. Okay, and you can